I'm Lee Huntsman, and it's a great pleasure to welcome you to this lecture series. 3 lectures, I hope you've got them all on your calendar. They're entitled Engineering Molecules, Tiny Solutions for Big Problems. As we're going to see, this is a vast arena of science, engineering, and potential. And these lectures are just going to open the windows on it a bit, but it's a fabulous topic and a wonderful lineup of speakers. So let me be blunt. Matt O'Donnell is a hero of the University of Washington. He is very accomplished, incredibly creative and versatile. And since he's been here, 6.5, 7 years? He's had an enormous impact across not only the engineering college, but across the university in his energy, his vision, and his ability to infect us all with that vision. His versatility is partly illustrated by the fact that we're here tonight. When he was getting ready to come to the University of Washington to be our new Dean of Engineering, he did enough homework about this institution and the alignment of its strengths with future opportunities that he crafted a vision. By the time he came in the door, he had a vision that has become molecular engineering and science. So 6 years later, we have a molecular engineering and science program. It's extremely exciting, and it already has enormous momentum. And most visibly, it has a gleaming new building just on the other side of Gerberding Hall that is home to investigators from a variety of different disciplines. It's not only a new laboratory, it's a new culture for doing this kind of interdisciplinary research. And the root of that is Matt O'Donnell's vision for this emerging area. So what is this emerging area? What is molecular engineering and science? Well, in one way, it's a little bit like science and engineering have always been, namely really creative people pushing the boundaries of science to develop new technologies and then bring them to application in the real world. But in another way, it's brand new. As you'll see tonight and in the subsequent lectures, this science is just mind-stretching. It's flabbergasting in some ways. The technology that can come from it is simply stunning. And the panoply of ways that it can be applied is just vast. So this is a very exciting field at a very exciting time in its development, and in a very exciting place that is going to lead us into this new future. And we're very fortunate to have as our guide into this new and emerging area none other than Matt O'Donnell. Matt, thank you.
Thank you. I want to have fun tonight, so please take it in that vein. I saw a couple of faculty members and others coming in tonight who know the science better than I do. Just suspend a little bit of disbelief tonight when we go through this, because it's more about what is possible, not what is the details of what's going on, which is really what I'm going to try to do. So let's go through the journey together, and what we're going to do is going to be 4 parts. The first part is I want to deconstruct this title, Molecular Engineering Revolution. So the first part is I want to talk about a revolution. What's a revolution? And I'm talking about a revolution in terms of a technical revolution. Okay, what does that mean? Second piece, I'm going to go through what is molecular. All right, I think you understand some basics about what it is, but I want to put it in the context when we eventually get to the revolutionary pieces. The other is something we all take for granted, is a very simple definition of engineering. And so I want to go through that definition because you may not think in terms of molecules and molecular systems that engineering principles apply, and they most certainly do. And so we'll go through that, and then we'll put it all back together again, which is to talk about why I feel we are at the cusp of a true revolution in molecular engineering and where it's going to go. And at the very end, we'll get some Star Trek videos and other things about where maybe it could go truly. Okay, so what is a technology revolution? Don't they look geeky? All right, does anybody know? Well, you can read the names up there. This is 1981, which is Carver, Mead, and Lynn Conway. And I brought with me, because I was about 29 or 30 years old when I bought this book, because what these two people, and actually Carver Mead, who was a Caltech at the time but now lives in Seattle, and so we see him around at events there, and Lynn Conway, who was a faculty colleague with me at Michigan in the 90s, so I've known both these people, is they created a book which was really the start of the, what I consider to be the start of the true IT revolution. Now, there was plenty of things in electronics and software and others that predated this. But this, to me, was a watershed because they really had sort of a systems approach with tools and the development of tools which allowed you to create things in integrated circuits. And with this, they started the revolution, which is now we would call the IT revolution. So I'm going to use the IT world as sort of an example or a model of how we define a technical revolution. So do you remember 1983? The good old days, right? Everybody, oh, good, I heard somebody. Everybody recognizes this. If you're under the age of 40, you probably don't have any clue what this thing was. Or you found it in a box when you were moving houses because your parents didn't throw it away. But that was the state of the art of the personal computer in 1983, and I had one. I remember that coming out. And this is a spec sheet. You can't read all of the spec sheet, so I'm going to put a pointer up here, and it's going to be on the left side. But just I'll give you one number here to look at, which is the memory was 64K. You're laughing. I remember when 64K, you're saying this, but I don't have enough stuff to fill it, right? Remember those? Okay. But also notice these price range up here, so I'm pointing at the top to the prices, is about the same as a PC that you would buy today. Okay, so that was 1983. Well, what was 1983? We had one other piece in there, and this is a little underexposed picture, but it's the Apple Lisa. Does anybody remember the Apple Lisa? Okay, did anybody own an Apple Lisa? I owned an Apple Lisa in 1983. You knew it was a prototype because my now 30-year-old son, at the time was 18 months old, got a paper clip into one of those disk drives and totally crashed the computer. And that computer was bought with General Electric money, so I was kind of in trouble. But revolution, it set a paradigm. So this was, the Apple invents the personal computer. But this is it. See that screen? Doesn't that screen kind of look like things you've been doing for a long time? Right? The drop-down menus, the graphics, all that. So this stuff was around 30 years ago. Right? So 30 years ago, the roots were set for going off for personal computing and integrating computation into your life. But it's very, very different now. Why is it so different? And so I have a phrase that a manager when I was at GE, so my first 10 years out of grad school was in company, I was in GE. And I had a manager then who has this little mantra, and I'm sure he stole it from somewhere, and I've never been able to find the original quote. So that's a homework assignment for all you. If you can find the original quote, please let me know so I can give proper attribution to this. But the first time I heard it was from a manager. And he was talking about what we're supposed to do as R&D engineers was to always look when a quantitative change leads to a qualitative change. Okay? That is, when does something, just by it goes faster or smaller or something like that, leads to a fundamental change in your life? Right? That's a revolution, as I would design it. So in this case, with IT, what is it that has changed? Well, it's changed, software and systems and the ways of thinking about it obviously have changed a lot. But that sort of fundamental screen and the way we interact and the way we think about it has been constant. What has changed is the speed of the processor, the memory density. So basically, the overall quantitative things that are going on in the computer. So here is an example just of a gaming computer. So remember, that was, the old Commodore was a gaming computer, right? You played Pong. Everybody remember that? Okay, that was on there. Versus now, and this is a 20 child, I'm not sure who it's from, you probably can read it better than I, but I'm pointing to the center one, which is the current gaming computer, and this processor speed is 4,000 times faster than that one from the Commodore. Okay? Not 2 times faster, not 5 times. It's 4,000 times faster. It's tremendously faster. Huge quantitative change. Okay, here's a spec sheet. Just like the spec sheet we saw before for the Commodore and for the Apple and those other machines, this is a spec sheet. So I'm going to point to the memory, which is the 4th row down, and so let's go over to the iPhone, because I have a feeling there's more iPhone folks in here than Droids. But if you go down, look at that memory. 16 gigabytes, right, versus 64 kilobytes. Kilobytes to gigabytes, right? You got megabytes in between. So it's almost amazing. It's like 250,000 times more. Huge quantitative difference. So why is it revolutionary? Because of the qualitative difference. That thing fits in your pocket. That thing's connected worldwide to information sources around the world. Does your everyday life change? I thought a very interesting statistics, which was about 2 weeks ago in the Sunday Times, which was that they polled office, where I forget where the study's from. So again, second homework assignment. Go find out where the study was from, because I've forgotten. But 84% of office workers polled within this study, random sample, in the United States, would go home and shut down if the internet went down, because they couldn't get any work accomplished. 84%. All right? It's this. It's a part of our lives. It's just why Lee joked in the beginning that the first thing he's going to say is turn these off, because it's hard to imagine us without these things around there. And it's not because it's the thing, it's what it connects us to. Right? That's a revolution. So what is a technology revolution as opposed to a new technology or something that's interesting or useful? It's when you have an area in which a quantitative change leads to a fundamental qualitative change in our lives. Okay? Just looking at some facial expressions, I think you get what I'm trying to get to with that. So let's move on. Let's move on to the second piece. Okay? What do we mean by molecular? All right? So, how many people took high school chemistry? What's a molecule? Buddy, what's a molecule? There you go, slide 1, bullet 1. Composed of atoms put together, right? Everybody knows that simple definition, but I want to expand on that a little bit to put it in the context of what we're talking about here in molecular engineering. And that is, you can think of it as really the basic building block of chemistry. In the same way you have tinker toys or other things that mechanically you can think of and you put together for a complex structure out of smaller subunits. You can think of the molecule as a basic building block of chemistry, and the way you put them together is not by machining or mechanically bringing them together, is by synthesizing. Okay, so a key concept that we have in molecular, as opposed to a lot of other areas of engineering and science, is that synthesis will be a key part. We're going to come back to that multiple times as we go on. The last piece is that you should also think about molecules as the basic building blocks of nanotechnology. You say, oh, wait a minute. I've read the articles in Scientific American and Forbes and others about what nanotechnology is. That's why I take silicon and I machine it really, really small. Okay, well, that's one kind of nanotechnology. But another kind of nanotechnology says, look, nano is just an exponent. It's 10 to the minus 9. It's a size scale. And molecules, especially many molecules that we find in nature, are exactly at the same size scale, and therefore can be manipulated in the same way. And I'll show you how they can be manipulated to do meaningful work. So a molecule, yes, we have our old high school definition up there in the top bullet, but we're also talking about it's your basic building block, and it's your basic building block that works on a size scale, which is down in the nanoscale. Okay? And you're going to build things up from that scale rather than machine things down to that scale. All right, I think we get the idea. Okay, the next idea within molecular, which I want to get across to everybody, is that Molecules, okay, high school chemistry again, right? We got to do a titration, right? You got an acid, but you drip it in there, you have the indicator color, it changes color, it's in there, and that's a chemical thing. But also, collections of different kinds of molecules, if put together in a particular way, can be also thought of as systems. And this, the way we as engineers think of a system, collections of parts that work together through a design methodology which perform a function. Okay, so here is a simulation of a large macromolecule that's found naturally in nature. It's an enzyme, I forget which one. If you want to find out, that's Jim Fander, who's a assistant professor in chemical engineering. And he did the simulations of this, and it's an enzyme. But what's interesting is, I'll just let this play, and I'll let you take a look and see if there's a piece of this that looks interesting to you. Okay? There's a hint in this. It's red. Okay? So you see it going up. So what it is, it's an enzyme. It's a natural enzyme. I think it's in the bacterium, but I'm not, again, sure, is that Jim's the guy to talk to. But why he did this is a very interesting enzyme, because the active site of the enzyme, that's the place that actually does the catalysis in the chemical reaction, is in this site right here. And why this is such a valuable enzyme is because this little flappy piece over here acts like a gate. All right? So when it's down, nothing can get in there, and nothing can react. If you open it, it's an active enzyme. Okay? Now, a lot of systems. I can see people's minds sort of spinning out there. Can you think of a system where if I had a gate in it, I could do some meaningful work? Right? Okay. Now, there's 2 points I wanted to get there. One is let's start thinking of molecules, not as mixing things. Whoops, I'm not supposed to go on this side. Mixing molecules about, just things that go together and change colors or change the flavor in some sauce. But to think about them as systems in the way we think about systems in terms of aircraft and electronics and cars and bridges and things, structures like that. The second part I wanted to get across with this is that is a simulation in the same way that you simulate somebody driving, you simulate flying an airplane, you simulate doing a lot of different functions. You're simulating how this molecule works. Why is simulation so powerful or so important? Is that you can predict how the thing's going to work. If you have a simulation of something, then you have an abstraction of how it's going to work. And once you have that, then you can stick it into stuff, because you can predict how it's going to work in stuff, and you can make more complicated things. Okay? So that's a tool. Here's another molecular system. And the bioengineers in here cannot say a word. Okay? Because they know this. And I'll tell you a little story about this, but I want you to just look at it first, and then I'll describe it. Now, it's a little bit fuzzy because this is an old video, but I apologize, but just... Okay, and then we'll go fast. It's just showing you stuff. I'll come back to what all this means, but just look at what it's doing. Now it's going to do it in fast cycle, how it actually works. Okay. So that thing is a motor. Right? What's a motor? Right? Converts some form of energy into a mechanical energy that provides either a force or a displacement that you have on an object. That's exactly what this thing is doing. So let me play it again. Okay, and this guy, so that's a inorganic phosphate, so this has to do with just the biochemistry. That's your power source. That's your energy source. The motor converts this change in energy, which is a biochemical source, into a mechanical force, which will push this object, and this will continue to process down this chain. Okay, it's just showing you one step. And so it's a motor. How many digital guys out there? A lot of digital guys, right? You know what a stepping motor is? You go step, 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 step. This is a stepping motor with about a 5 nanometer step. Okay? It's 50% efficient in going from chemical energy into mechanical energy. All right? You know what it is? It's a muscle, okay? Actin myosin system. So something that nature produces. There is a whole collection of motors, molecular motors that you find in nature. There's rotary motors. There's translational motors. Okay. So again, that's a system, though, right? It's a system that provides a function. In this case, it's from nature. It's the muscle that's sliding two filaments across each other and providing force, okay, which is the muscles that you have and that I'm losing rapidly. Okay, and the last one is non-biological, and it's a little complicated, but let me just try to get the idea across. This is about when you get yourself a new molecule that's really cool, but you can't get it to fit in something that is productive at all or is useful at all. So there's, and this is from, I'm sorry, I should say who this was, because this is local UW. This is from Alex Chen, who's the department chair in material science and engineering, okay? And what he has done is there's these class of molecules which are really, really cool. That little vector there is something that says that I can bend, the simplest way to think about it is I can bend light very effectively, all right? So if I bring light into this object, wherever that arrow is going, the light will be bending that way. It's not exactly doing that, but it's close enough that, for the argument, all right? The problem is, if you stick a bunch of these molecules into just some material, is you get the arrows bending all different ways because it's just in there randomly. You just brew it together in there randomly. So when you stick in light, it's going all over the place, and there's no meaningful work that's done there. What Alex did, and his team, came up with an idea of a molecular system, saying, okay, I got this molecule, but what can I synthesize that will attach to that can provide a lock and a key? So that when these molecules come together, they won't randomly do it. The key will find the lock, and then the next key will find the next lock and the next key. And so let me go through that, the steps of how they do that. So first thing you do is you heat it up so the molecules are bouncing around all over the place. You then put an electric field on there. Why the electric field? Because the electric field will force them all to line up. You then cool it, take the electric field off. Note here, and this is just cartoon style, you got all the purples on one side and all the grays on the other side. You have the lock and the key. So when you force them to align with that electric field, the lock had to go into the key, the lock had to go into, or the key had to go into the lock, the key had to go into the lock, the key had to go like, they're locked now, so I take away the field, I cool them off, they're stuck. Okay, that now is a material, and that's a commercial material. It's used in electronics right now for optical devices, for switching, okay? That's molecular systems. You take individual molecules together, you engineer them so that they provide a particular function that can be, in this case, is a macroscopic function. It's in a chip, you use it for optical switching. Okay, that's a little geeky, so that's where we'll stop for now on the molecules. But I think from your facial expressions, you kind of get the idea of what we're talking about, is the ways in which molecules can come together as you're looking for functions. Okay, so now let's go to the third piece. What is engineering? So I'm going to point to these pictures up here. Anybody have a clue who that guy is? Any Boeing? Oh, I got an answer, yes.
Von Karman.
Exactly, it's Theodore Von Karman, okay, who was both a rocket scientist and an aerospace engineer, okay? And so he has a quote I use all the time because I love it, because he's somebody who spanned the two worlds, which I hope is what we all try to do as engineering faculty, is span these two worlds between science and engineering. His quote, which I love, is that scientists discover the world that exists. Engineers create the world that never was, right? We make new things, right? The bridge didn't exist without engineering. The car doesn't exist without engineering, right? Okay. But it's driven by science, right? So the discoveries that we find in science become new tools for us to engineer the world, so to create new things. So let's look at this a slightly different viewpoint. Another way to think it is that engineering uses a design methodology, right? This idea that you're going for a particular function. You're going to design, you're going to shape something to a particular function. So it uses a design methodology to apply science to society's needs. We solve problems. We always say that all the time, right? Engineers are problem solvers. And that's, to me, what it means, is you have a design methodology which allows you to apply science to society's needs. And a more formal way is, and I'm going to rotate through this, is the engineering design process. So number one, you identify the problem. Number two, you identify criteria and constraints. Very big concept in engineering, right? We don't have the spherical chicken, right? So you have constraints. You have to brainstorm possible solutions. 3, 4, generate ideas towards solution. 5, explore possibilities. 6, select an approach. That's usually when a manager shows up. Number 7, build a model or a prototype. It doesn't work, so you go to number 8, which is refine the design. You keep going around that cycle. And the way I always think about it is you keep going with, you keep reducing the radius, right? So you're going around that, and so it's a spiral to eventually you get to a design which actually satisfies a societal need. So I think all of us as engineers and trained as engineers get that feeling. You know what that means. And even us who just do work in our houses without formal engineering training get this idea of this iterative process of doing it, but focused on a particular function, a particular need. Okay, so what is molecular engineering? So molecular engineering describes, and I'm going to highlight this here, the synthesis again, okay? Not machining, but synthesis of new functional molecules, like that guy with the big arrow, right? Of new functional molecules and molecular systems. Then the second word to highlight, designed to meet a specific application. Right? Does that make sense? Doesn't it sound like engineering? Right? The only thing that's really different from a standard definition of engineering is this synthesis piece. Okay? Although in chemical engineering and other things, synthesis have been around a long time, but this is the driver. The whole idea here is that synthesis will drive the entire process. So we'll now go into the last piece, which is the longer piece we'll go into now, is addressing that molecular engineering revolution. Okay? And what I'm going to try to argue, so I'll start with my conclusion and then try to go through the argument, is that I believe the University of Washington has placed a huge bet that it's 1980 for molecular engineering. Okay? That we will have the equivalent of this is where we are and where are we going to go. So let's talk about that. So the first part of the revolution is the bet. And I love this because this has been 7 years of my life. This is a time-lapse photograph, so as we go through, is the building of the Molecular Engineering and Sciences building. It has some interesting parts. As it goes up, if you look to the right, you'll see all this construction going on over there that pretty soon will be buried. And that's because we have a huge basement in this building, which is a molecular analysis facility. And it'll be the largest one. Actually, the architect tells us it's the largest one on the West Coast of this type. I don't know who's on the East Coast that has a bigger one, but anyway, that's what they said. On top of it is a laboratory building, which has a lot of neat characteristics, which I'll go into in a minute. And pretty soon this will end. And you'll see at the back, well, you didn't see the back of it. And that's where you are now. So here it is, the Molecular Engineering Sciences Institute. The institute, which is larger than the building, has 14 departments. 14 different departments are represented. Everything from computer science to chemical engineering to biology is involved. There's 75 faculty members associated with the institute now. This basement is this molecular analysis facility. We already have 4 major instrumentation centers that are in that basement area, and we have 3 national research centers already in there, and we're competing for our 4th next week, which will be very exciting. The building itself, and it's nice view outside, nice aesthetics, but the part I like the most is the inside. The inside is clearly one of the most flexible spaces. I know it's just won its first design award. I'm sure we're going to see multiple design awards happening over the next year or two, because this is a heavily instrumented laboratory that's totally modular. You can pull out benches, you can stick in wet labs, you can move people around literally in hours rather than weeks or months. Okay? The second is that the spaces where people have their desks and doing like the computational work and the like is totally open. Again, very, very flexible and set up kind of in a collaboratory approach, meaning that people are in sort of little clusters where they're going to do work together. It's very, very different than a traditional office and very, very different than a traditional lab. And it's a wonderful feel. The part I like as an administrator is there's twice as many people in that building as our average building. Okay? And they love it. It's very, very efficient. Okay, so we're betting on this. UW is very much betting on this, and we've gone and done this institute because we think we are at that point where we're going to start to see the quantitative changes leading to real things. So I'm going to go through 3 areas here. I think I can do it in the time. The first 2, Biotech Theme and the Cleantech Theme, are the major themes that are in the institute now. Okay? Then at the end, I'm going to look, and I'm pointing here to the bottom arrow, these things, the other applications. These are the things which are out there. And I'm not sure whether I should say hold me responsible and nobody else, or don't hold me responsible because it's so far out there. But I just wanted to make you sort of think where the possibilities are. That's the analogy between that Commodore 64 and the cell phone that you carry around now. Okay. So first, the biotech. And these are 4 of the major players who are in the building in the biotech theme. So I'm going to point to them from the left. Starting is Pat Staten, who's the director of the overall institute as well. Susie Punn, who's in bioengineering. Dave Kastner, who's in chemical engineering and bioengineering. And David Baker, who is in biochemistry. And what things do they do? Well, there's a ton of stuff they do. So I took just a couple examples of what they do. So here's one. Have you had a loved one who has gone through chemotherapy? Okay? Not very nice experience. Why? Because the fundamental chemotherapy is you're going to kill cells, but because cancer cells metabolize a little faster, you're going to kill them a little faster and you kill everything else. Not really a well-designed, engineered system. Okay? So what Pat and Susie and others who work in this idea of targeted drug delivery is that why not have something which is a drug which can kill those cells, but let's find a way to only get them to the cells which are cancerous rather than to all the other cells that are in the body. And the way you do that is by creating systems, so I'm pointing up to the top here, systems of molecules which mimic the way things get into your body now. How does a virus, for example, get from your nose or your mouth or something like that into a specific cell where it does its work by trying to reproduce itself? How does the virus get in there? The virus is a molecular system. All right? So it goes from the outside world and goes through multiple levels to eventually get inside your cell, to get intracellular for there. So Pat has this nice little graphic, and I like to use it to try to describe how to do this design. So we have pathogens. So again, think of it as a virus. And you get your virus out, and somehow it's got to get through the system. So it has to get through your blood system, has to get through the tissue barriers, into specific cells, get into the cells, and then use your, it's the free lunch, right? The virus comes in, all it does is use your DNA to reproduce itself. Not very thoughtful thing, right? But a very smart thing, right? Because it's able to get through this. And so I think this is animated. Yeah. So when you actually put that to scale, that when this goes through, that this system can traffic. That is, it can get through the vasculature, get through the tissue, and get inside the cell target. Why? Because it has specific molecular species on the surface of it which tell the system, let me through, right? To get outside the vasculature, to what's called extravasate. So it gets outside the vasculature. To get through tissue. To get to a particular cell, the cell has a receptor that says, yes, that's something they want, and then brings it into the inside of the cell. Okay. So can you use that same idea, but you control, so you design the effective pathogen, except that has these types of markers which will allow it to go through this system, except inside you don't have a piece of DNA that you just want to have it replicate itself. You have a drug, or you have some kind of therapeutic agent that can get in there. So you can use that same approach of a molecular system, so it has all these different signatures on there which allows it to be recognized and passed from the blood through the tissue. But then when it delivers, it's going to deliver the drug to that cell. And it's targeted in the sense as those signatures are specific for tumor cells are different than other cells. So if you design that optimally, it will get just into the tumor cells and not into any other cells. All right? I think from your faces you get that idea. So that's an engineered system with a function which is to deliver a cargo, which in this case is a drug, which will be used to treat cancer. Okay. Another one. Remember I showed you that little enzyme that was flipping around and these tools that you have for the molecule. So let's use tools, computational tools, driven by a fundamental understanding of the biochemistry, but tools to design proteins which don't exist in nature. Okay? And David Baker is the guy who's doing this. And he's had this tremendous success with a software tool which is widely distributed and used around the world now, both in academics and in drug developments and biotech industry, of being able, from first principles, to design custom proteins. Okay? And he keeps setting sort of land speed records every few weeks of a different application that they designed a protein to. So the example I have here is one that was designed to go after one of those viruses, but the exact place which allowed it to get inside the cell, this designed protein would come in and just attach to that point. So even though that virus could get all the way down to a particular cell, it could never get inside the cell. And so he's designed, again, design function. He's designed a novel protein using computational tools that binds to a particular flu virus protein and prevents its entry into the cell. So it prevents infection. Okay. So that's biotech. The second major theme is cleantech. And the folks that we have here, there's, again, a set of 4, and they share a floor in the molecular engineering building. And we have Dan Gamlin, top left is Dan Gamlin, lower left is David Ginger, who are from chemistry. You have Christine Luscombe, who is from material science and engineering, and you have Hugh Hillhouse, who is from chemical engineering. So what are these guys doing? Okay. So it's solar cells. Does everybody know how a solar cell works? Okay, that's why I put this graphic up. So at least I found it's valuable. Okay, so solar cell, in principle, is complicated, but in one piece of it is complicated. The rest of it's pretty simple. And the idea is you have light coming in to a material. In this case, it's a semiconductor material. It has to be able to split positive and negative charges. Okay, that's what a semiconductor can do. You have a doping, a p-type or an n-type, for those who are electronicers. That's in there. When the light comes in, the reason why you can't see through, your hand or something is that the light is absorbed. It can be reflected too, but mostly absorbed that's in an object. So when the light comes in, it's absorbed. But in the semiconductors, when the light's absorbed, it creates this little bundle of positive and negative charges all together. It's called an exciton, but it's together that's in there, which then, when it hits this barrier between one type of semiconductor and another type of semiconductor, splits that charge into a positive charge and a negative charge, which by definition will flow the opposite direction. Okay, so it converts light into these two charge pairs, which then can flow and create a current. And that's the power that you get, that you use for your electric lights or for batteries, whatever you're going to do. Okay? So solar cells are cool. They're clean. No fossil fuels other than what's taken to manufacture them. But they're expensive and exotic. All right? So the standard types you will get are single crystal silicon of relatively large thickness and surface areas, which are very, very expensive devices. Anybody have solar cells on their house? You live in Seattle. Do you know what kind of technology you have? Is it silicon? Yeah, okay. More recent developments have been in what are called multi-junction devices or thin film devices. But there's a new wave that is coming, which are photovoltaics, which are solar cells. They're made from plastic. Okay? And so let's go through that a little bit. And there's also solar cells which are like of this type, which is a multi-junction, but using a totally different process, which is very, very similar to printing paper. So let's look at that. So here again, here's this solar cell that has this electron donor and acceptor, so P's and N's, and this is the traditional solar cell. However, you can make an organic material. This is a polymer. It has multiple types of molecules in there that are engineered that can carry the positive charge and the negative charge a different way. Now, you can't make a single polymer that has this kind of layered structure in there and expect the charges to move efficiently and quickly like they do in the traditional semiconductors. So you have this modeled structure. That's the engineering design that's involved in making one of these things. But the point is that this stuff is just a plastic sheet. It's saran wrap, effectively. A similar process, or I should say an analogous process that is done, but Hillhouse does, is to make these multi-junction types of devices, but to do it by impregnating ink with a particular types of crystals, which are just from naturally abundant materials that you find around, that when they go in the ink, they self-assemble into a layer, which is exactly this multi-junction device that you'll have for solar cells. Okay? So that's a little geeky, I agree, but why is it cool? Because, and my wife's around somewhere, there she is my wife's a newspaper reporter, ex-newspaper reporter now, that's in there, and her old newspaper, which is defunct now, has one of these things just sitting there called a printing press. Okay? Well, to make the solar cells that we saw that was talking about the ink ones is almost an identical process to what you would have for printing. So I thought this was a new investment opportunity out there, is to convert the defunct newspaper printers into solar cell printers that's out there. It's funny, but it's almost real. Okay? And this is the type of stuff that Hugh does. What I don't have a slide for is, with the organic ones, it really is saran wrap. So the basic process is a rolled plastic type of process. Again, not exactly the same. So it's, can you have these large areas of cells very, very cheaply? Well, can you have a lot of saran wrap very, very cheaply? So pretty cool stuff where it's going to go. Okay, in the last few minutes, though, now I'm just going to talk about the other stuff, which is a little bit out there. So let's think about, the future, and everything's made of stuff, right? But what would happen if you had stuff that could heal itself? That is, you broke something, you scratched it, you did something like that. What if the material itself could adapt and fix itself? You say, that's wild. What would do that? Your human body does that, right? Routinely does that. And what we're starting to see is that concept extending to more mundane things, and this is a nice video. I love this guy's accent, by the way.
You find a nasty scratch on your new car. Now what? This research team at the Case School of Engineering found the key.
We came up with this idea to basically develop a coating that if it was scratched, you could simply take out a light and heal the scratch.
Stuart Rowan's engineering team had already developed a material for a separate use, but surprisingly had all the necessary components for this endeavor.
Just as a quick experiment, we took out a razor blade and deliberately scratched the material and then put it under a UV light. And within 30 seconds, the scratch had disappeared. That was the eureka moment. That was like, wow, we've got something that's really cool here.
So, what's the scientific secret?
So what we've developed is essentially a new plastic material composed of very small chains that stick together.
Molecular
and
system?
assemble into much larger chains. But what we've designed into the molecule is essentially the ability for it to disassemble on exposure to light. When
So
it disassembles, the material flows into the crack and the system gets
And then it
healed.
reassembles.
And the discovery is just scratching the surface of possibilities.
And so let's extend this now to the last piece, which is stuff, is the idea of the Industrial Revolution and all of manufacturing is that producing, taking materials and producing things which are useful devices, okay? And so what I would say is the traditional stuff is machining and assembling, right? And it's now, a lot of it's robotized, computer controlled, but it's still fundamentally machining and assembling. And so this one doesn't have sound. But this is what we're used to. When we think of manufacturing, this is our sort of traditional mode, right? You machine something, you assemble it, it's robotized now, but an assembly line comes down, and it's to a particular design, and out comes a useful product for what you want. Okay. But new stuff. Remember synthesis we talked about, that keyword synthesis? So let's take that for 2 steps, and then I'll conclude. First step is real assembly. And it does come from UW, see UW TV. And I'll just play it, and you can listen to where the next, I think the next level of manufacturing is going.
So large that oftentimes students have no idea of the amazing research that's taking place. Such is the case with the Solheim Lab. This lab uses and develops printers that build objects using a process called additive manufacturing. Mark Ganter, one of the professors here, led us into his
That's an
secret
old
lab
building,
in
by the way.
Part of the mechanical engineering building.
It needs
for
to be
the
modernized.
You're standing in the Solheim lab. We have about 10 different additive manufacturing processes. We can print in a dozen kinds of plastic. We can print in about 20 kinds of ceramic.
Did you
We
hear
can
that
print
verb?
in about 50 total
Print.
kinds of powder, including metals. Any piece of geometry you can imagine, we can model. Additive manufacturing basically deposits thin layers of an object. So if you made a computer model of an object, it would be sliced into very thin layers. Then a process would build the object by producing each single layer at a time and then adding them up as a stack.
If you look at this,
Get
for
that?
the bottom cross section, you're just going to have a circle. For the next one, it's going to be a bigger circle. And then slowly, as you put all these cross sections together, you get an object. Hence additive manufacturing, adding it layer by layer.
Machining, negative manufacturing. Start with something, you take away material. Okay? This is additive manufacturing. You start with nothing other than a computer model, and then you start to print, but you print layer by layer by layer with materials which then will self-interact and will assemble into something that you saw there. So we see that step. So what is the next step in this progression? What I would argue is the logical next step, and that's self-assembly. Okay? That is, the material itself is programmed to assemble itself. Right? You say, wow, that's crazy again. No, because we have a wonderful example from nature again. Right? Right? Remember, that's from a single cell. Right? That you go from that into a functioning human being. Right? That's 100% self-assembly. Using the energy sources that are around you, using the materials that are around you, but the program is a molecular program which is embedded into nucleic acid. All right? So it self-assembles. So we don't understand that to the level that we can assemble what we want, but there's principles in there, and I'll just show you some very simple examples and build up of how this can be used for simple manufacturing. This is Eric Clavin, down in the bottom left there, and he's an electrical engineering professor. Notice when I was going through this, there's a lot of different departments, a lot of different areas that are in there, and because this is the nature of this field, is because it's engineering and systems, but it's also chemistry and synthesis. Okay, so Eric Clavin, who's a systems guy, electrical engineering, did a very simple thing a number of years ago where he set up just to prove a principle, is that he set up a set of simple triangles, and then he programmed the surface interactions to mimic a particular chemical interaction that would preferentially, he showed it just from these local things, and he did a mathematical model to prove that this thing must assemble as a hexagon. Okay? So I'll play it. And this is on an air table. So he's blowing it around, so it's randomizing these guys. And they're bouncing in interaction. That guy looks close, right? Oh, but it can blow apart. Why? Because it's not a hexagon. So they bounce around. Oh, that guy's a hexagon. It will never change. Okay? Because it's programmed to go to a hexagon. All right. So I think from your faces you got that idea. The program's built into the material. It's very simple, but where can you go? Well, you can go to the next level, and this is something from, ooh, that really is fuzzy, sorry. But that's Carl Boehringer, who is also in electrical engineering. He's the head of our microfabrication facility. He has a very, very simple idea that works really cool. He's trying to assemble, ultimately, these are just little discs he's doing this, but he ultimately wants to assemble integrated circuits so that you would have little circuits, but then to make a circuit board, it would all just self-assemble itself, okay? And the way he does it, he has two competitive processes. One is this top thing is trying to polymerize, but it's being inhibited by the bath. Only when you get a complete set of devices that fill in all that space, it's allowed to polymerize to the next step. And you'll see it will go chunk, chunk, because it can fill in only when all the pieces in the row are filled in. Okay? So there's no robot pulling this thing. You feel like you're dragging the thing up. It's not. It's the top piece is polymerizing down while the bottom piece is being agitated. And it will only fully polymerize once it's fully populated. Okay? So it's a fairly complicated thing. It's self-assembled. You don't know it. Okay. Before I do the last piece is, the reason I use those examples, simple examples, there's two major principles involved in self-assembly. First principle is, it's not fixed in time. Right? When you think of machining, it's tick, 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 right? When you think of a computer, it's a clock cycle, tick, tick, tick. This is random. Sometimes it goes, sometimes it doesn't go, right? Because the program's in the material, it's only when conditions are right that it will assemble and then move on. Now, in aggregate, you can have an average speed, but you're going to have fluctuations in that. So it's the number one thing. The second thing is it's massively parallel, right? I don't need all this apparatus around it. Now, you do for the positive printing, but once you truly self-assembled, I can put my vat of stuff here, I can put my vat of stuff here, I put my vat of stuff here, I can put it anywhere, right? And it will all self-assemble. So let me conclude. Molecular engineering revolution, this is, what was the Yogi Berra quote about, is it prediction or? No, prediction is very hard, especially about the future. The Yogi Berra quote. So I'm going to take a shot at this, but I think there's a couple simple principles, and that's what I want to end on. That there's going to be a relationship. So I've talked about stuff, but IT is out there, and the IT revolution is going to continue. And IT will provide the tools, and it's the basic science that leverages IT tools, which will allow us to capture molecular information as stuff. And that's why I was showing you those molecular simulations, so you can see, and that's going to expand greatly, is our understanding. So we're going to have tools, just like the tools that were developed for this, okay, that will allow us to capture the information that is in stuff. Molecular engineering will provide complementary tools to convert that molecular information into real products. And I think self-assembly is just an example. There's many, many other examples that will go in there. So the question is, when will a quantitative change in these two tools lead to a fundamental qualitative change that changes your quality of life? I don't know. But there's one thing I know for certain, that UW is going to be right in the middle of that. Okay? because of what the history has been here, and I think what we've tried to set up with the building and the institute to bring people together to focus on, we're at 1980, how do we accelerate and actually get real applications out there to change the world? So I'll end with that, and thank you very much.